Again, welcome to operating system. This is CS332 class. In these lectures, we're going to discuss about threads. And these lectures cover chapter 4 of our course textbook. In our previous lectures, chapter 3, we discussed about process. And we say a process is a program that is running or a program that is executing. So a thread also is a program that is executing, but a thread will be a mini process, which means, again, one process can have two or more threads. So all the characteristics of a process is almost the same as a thread. So the discussion so far has presented the concept of a process as embodying two characteristics, that is resources ownership and also scheduling and execution. So a process includes the virtual address space to hold the image or the process image. If we can recall this in chapter 3 of our course textbook, we said the process image is the collection of program, stack, data, and attributes that define in the process control block. So from time to time, a process may be allocated control or ownership of resources, such as the I/O channels or the I/O devices, files, or a main memory. So again, a process may allocated control or ownership of any resources. Now, the OS normally performs a protection function to prevent unwanted interferences between processes with respect to resources. Now, with the scheduled execution, normally we know the execution of a process follows an execution path, which is the trace, through one or more programs. So this execution may be interleaved with that of other processes. So we can say a process has an execution state, such as running or ready, and also a dispatching priority, and is the entity that is scheduled and dispatched by the operating system. Now, the unit of dispatching is referred to as the thread or lightweight process. So as we said, again, process and thread have almost the same characteristics, the same function, everything. But a process, or we say a thread, is a lightweight process, which means, again, a process can have many threads. So some unit of resources ownership is referred to as a process or a task. And also multi-threading means the ability of an operating system to support multiple concurrent paths of execution within a single process. So which means we have a single process that is executing, but it may have multi-threading, which means it can have two or more threads. Each thread will be a task, which normally will be executed concurrently. So some thought should convince us that these two characteristics are, again, independent and could be treated independently by the operating system. And this is done in a number of operating systems, particularly recently developed systems. Now, to distinguish the two characteristics, the unit of dispatching is usually referred to as the lightweight process, while the unit of resources ownership is referred to as the process or the task. So again, multi-threading refers to the ability of an operating system to support multiple concurrent paths of execution within a single process. So here we have a very good example, a traditional approach of a single thread of execution per process. Here, in which the concept of a thread is not recognized. So here we have one process, one thread. And this section we have multiple process, that's one thread per process. but we may also have one process with multiple threads. So here we have one process with 3 threads, or we may have a multiple process with multiple threads. So again, the traditional approach of a single thread of execution per process, in which the concept of thread is not recognized. This is referred to as a single thread approach. So on our left side, again, we have a single thread approach. Now, 2 arrangements show in the left half of this, our figure 4.1, a single threaded approach. So Microsoft DOS or MS-DOS is an example of, again, operating system that supports single user process and single thread. Now on our right side, again, we have the multiple thread. We can have a single process, multiple thread, or multiple process, multiple thread. So other operating systems such as Unix support multiple user process, but only support 1 thread per process. And the figure here again shows multi-threading, threaded approaches. So a Java runtime environment is an example of a system of 1 process with multiple threads. Also of interest is the section and the use of multiple process of which support multiple threads. And this approach again is used in Windows, many modern versions of Unix and Linux operating system. So in this session, we will give a general description of a multi-threading and also the details of Windows, Solaris, and Linux approach will be discussed later in this chapter of our course textbook. So again, in a multi-threading environment, a process is defined as the unit of resource allocation and also a unit of protection. So again, the following are associated with process, the virtual address, space that holds the process image, and also the protected access to processes or other processes. Also the inter-process communication, files, the I/O resources, such as the channels and the device. So from here, we say the right half of the figure 4.1 shows the multi-threading approaches also. And Java runtime environment is an example of a system of process, 1 process with multiple threads. So process is defined, as we said again, in a multi-threading environment as a unit of resources allocation and also unit of protection. So we have 1 or more threads in a process. So again, within a process, there may be 1 or more threads, each with the following. Every process, 1 or more thread. At least we may have a thread execution state, which can be running or ready, and also a save thread context when not running. One way to view a thread is an independent program counter operating within a process. Also, we may have the execution stack or some pair thread stack storage for local variables. That again, some pair thread static storage for local variable. Also, access to memory and resources of its process share with all other threads in that process. So again, 1 or more threads in 1 process or in a process. Now each thread may have all these characteristics. So that's example here in this figure here shows the distinction between thread and process from the point of view process management. So we have single thread process model, multi-threaded process model. So we can see in one system, we have different threads. See, each is a thread. And we may have the thread control block with the user stack and the kernel stack. Also the process control block and the user address space. And this is a single threaded process model. So in this case, we have only one thread. In our right, we have multiple threads. So the representation of a process include its process control block and also the user address space, as well as other user and kernel stacks to manage the call return behavior of the execution of the process. Now, while the process is running, it controls the processor registers, and the content of these registers are saved when the process is not running. Now, in a multi-threaded environment, there is still a single process control block and also a user address space associated with this process. But now, there are separate stacks for each thread, as we can see in the diagram. We have single process control block, user address, but each thread have its own user stack, kernel stack. So the key benefit of threads, here we say, based on this concept, all of the threads of a process will share the state and also the resources of that process. So we have one process, it may have 10 different threads. All the threads must share the same state and the resources of that process. And they reside in the same address space and also have access to the same data. All the thread may have access to the same data because they all belongs to the same process. Now, when one thread alters an item of data in memory, then the other threads see the result if and when they access that item. So again, if one thread opens a file with read privilege, other threads in the same process can also read from that file. Now, the key benefit of thread derived from the performance implications. So one is it takes far less time to create a new thread in an existing process than to create a brand new process. And also a studies was done by Mac developers, which shows that the thread creation is 10 times faster than a process creation in Unix. Also, the second benefit, it takes less time to terminate a thread than a process. And third, also, it takes less time to switch between two threads within the same process than to switch between processes. And lastly, the thread enhances efficiency in communication between different executing programs. So in most operating systems, communication between independent processes requires the intervention of the kernel to provide protection and mechanism needed for the communication. However, because threads reside within the same process and they share the same memory and files, they can communicate with each other without invoking the kernel. So here we can say, if there's an application or a function that should be implemented as a set of related units of execution, it is far more efficient to do so as a collection of threads rather than a collection of separate processes. So that will be, again, the main key benefits of threads. And so thread use in a single user system. Here we say that there are 4 different, again, examples of the use of threads in a single user multiprocessing system. So the first would be the foreground and background work. So for example, in a spreadsheet program, one thread should display the menus and read the user input, while another thread will execute user command and update the spreadsheet. This arrangement often increases the perceived speed of the application by allowing the program to prompt for the next command before the previous command is complete. And second is asynchronous processing. So asynchronous element in a program can be implemented as threads. For example, as a protection against power failure, one can design a word processor to write its random access memory buffer to disk once every minute. So a thread can be created whose sole job is periodic backup, and that schedule is set directly again with the operating system. So there's no need for a fancy code in the main program to provide for time checks or to coordinate input and output. Also, the speed of execution is good. A multi-threading process, again, can compute one batch of a data while reading the next batch from a device. So on a multi-processor system, multiple threads from the same process may be able to execute simultaneously. So even though one thread may be blocked for an input and output operation to read in a batch of data, another thread may be executing. And also the modular programming structure. So programs, again, that invoke a variety of activities or a variety of resources and destination of input and output may be easier to design and implement using, again, threads. So again, in an operating system that support thread, scheduling and dispatch is done on thread basis. Again, because of the efficiency and the speed also. So most of the state information dealing with execution is maintained in the thread level data structures. But also there are several actions that affect all of the threads in a process, and that the operating system must manage at the process level. So for example, suspensions involves swapping the address space of one process out of main memory to make room for the address space of another process. Because all threads in a process share the same address space, all threads are suspended at the same time. Also, termination of a process terminates all the threads within that process. So if we have 4 or 5 threads in one process, when the process is terminated, again, all the threads within the process also will be terminated. So thread execution states, and the key states for thread, again, the running, ready, and also block. And also we may have thread operations that are associated with change in thread states, such as the spawn, block, unblock, and also finish. So typically, when a new process is spawned, a thread for that process is also spawned. Subsequently, a thread within a process may spawn also another thread within the same process. So providing an instruction pointer and argument for a new thread. The new thread is provided with its own register context and a stack space and placed on the ready queue. When it comes to blocking or block, when a thread needs to wait for an event, it will block or save its user registers, program counter, and stack pointers. So the processor may now turn to the execution of another ready thread in the same or a different process. Unblock is when the event for which a thread is blocked occurs. The thread is moved to the ready queue and is unblocked. And when a thread completes, its register contexts and stacks are dead located. And this will lead us to the finished state. So this is an example we have here. So again, the significant issue is whether the blocking of a thread results in a blocking of entire process. In other words, again, if one thread in a process is blocked, Does this prevent the running of any other thread in the same process, even if that other thread is in ready state? So some of the flexibility and the power of thread is lost if one block thread blocks an entire process. So again, when returning to this issue, subsequently, our discussion of a user level versus the kernel level threads. But for now, let us again consider the performance benefits of threads that do not block an entire process. So we can see again, the diagram here shows a program that performs two remote procedural calls. So we have the remote procedure RPC requests for two servers, two remote procedural calls to two different hosts to obtain a combined result. So in a single threaded program, the results are obtained in sequence. So the program has to wait for the response from each server in turn. But we can rewrite the program to use a separate thread for each remote procedural call result in a substantial speed up. Now, if this program operates on a uniprocessor, the requests may be generated sequentially and the results processed in sequence. However, the program waits concurrently for the two reprise. So again, one uniprocessor multi-programming enable the interleaving of a multiple threads within the multiple process. So in this example, we have, for example, 3 threads, A, B, and C, process 1, 2, and 3. In a three thread in two processes are interleaved on the processor. So here execution passes from one thread to another, either when the currently running thread is blocked or when its time slice is exhausted. So this is a blocking stage, ready stage, and also the running. Now with thread synchronization, here we say all of the thread of a process share the same address space. As we said earlier, all threads of one process may share the same address space and other resources such as, again, open files or main memory. So any alteration of a resource by one thread will affect the environment of the other threads in the same process. So it's therefore necessary to synchronize the activities of the various threads so that they do not interfere with each other or corrupt the data structure. So for example, if two threads each try to add an element to a double linked list at the same time, one element may be lost or the list may end up malformed. So the issue raised and the techniques used in the synchronization of threads are in general the same as for the synchronization of process. And again, we will cover this concept in our textbook, again, chapter 5 and 6. So any alteration of a resources by one thread will surely affect the other threads in the same process. So this is why, again, we need thread synchronization. So we have two types of threads, the user level thread, and also we have the kernel-level thread. So again, there are two broad category of thread implementation, either the user level or the kernel-level thread. So they are also referred to in the literature as the kernel support threads or lightweight process. That is the kernel-level thread. So we shall go through each one. The first is the user level thread. So again, in a pure user level thread facility, all of the work of a thread management is done by the application, and the kernel is not aware of the existence of threads. So this diagram can illustrate the pure URT. So the thread library files, we can see the user level at the top, kernel level down. Again, all the thread executing, they don't have any direct access or interfere with the kernel space. So sometimes we may call the user level thread as a very secure thread. So again, all thread management is done by the application. The kernel is not aware of the existence of those threads. So again, any application can be programmed to be multi-threaded by using the thread libraries, which is again the package of a routine for user level thread management. And this thread library contains code for creating and also destroying threads, also for passing messages and data between threads, for scheduling thread execution, and also for saving and restoring the thread contents. So again, by default, an application begins with a single thread and also begins running in that thread. So if an application begins with a single thread and begins running in that thread, this application and its thread are allocated to a single process managed by the kernel. So at any time that the application is running, the process is in the running state also. And the application may spawn a new thread to run within the same process. Spawning is done by invoking the spawn utility in the thread library. Also, the control is passed to that utility by procedural call. And also the thread libraries create a data structure for the new thread and then passes control to one of the threads within this process. And that process is in the ready state using some scheduling algorithm. So again, all of the activity described in the previous section slides, again, takes place in a user space and also within a single process. So again, this is, So again, this example of a relationship between the user level thread state and also the process. So we have thread 1, 2, but both thread are in process B. So process B have to be in running state with the threads. And now process B is in block, but again, our thread 1 is still ready, thread 2 is running. Then when process B is in ready state, we have thread ready and running, etc. So the whole concept here is that the application executing thread 2 makes the system call that blocks B. So thread 2 make again block B. So again, all of the activity described in the previous slides again take place in the user space and within a single process. Now the kernel is unaware of this activity because this is a user level. And also the kernel continues to schedule the process as a unit and assign a single execution state, either ready, running, block, etc., to that process. So the example here again, number 1, we have application executing thread 2 make system call that blocks B. So for example, an IO call is made and this causes control to transfer to the kernel, and the kernel invokes the IO action, then places process B in the block state, and then switches to another process. Meanwhile, according to the data structure maintained by the thread library, thread 2 of process B is still in the running state. So this is important to know that thread 2 is not actually running in the sense of being executed on the processor, but rather it is perceived as being in the running state by the threads library. So the corresponding state diagram are shown here in B. We can see after some system call, process B was blocked, but we have thread 1 is still ready, but thread 2 is in running state. Now, let's say we have a clock interrupt passes control to the kernel, and the kernel will determine that the current running process B has been exhausted its time. So the kernel now places process B again in ready state and switches to another process. But meanwhile, according to the data structure maintained in the thread library, thread 2 now of process B is still in the running state, and the corresponding state diagram shows here. Now, thread 2 has reached a point where it needs some action performed by the thread 1 of process B. So action must be performed by thread 1 of process B. So thread 2 enters a block state, and then thread 1 transition from ready to running state, which is the transition from, again, ready to running. Now the process itself remain in the running state, and the corresponding state diagram is shows here again, 4.6D. So we can know that each of the 3 preceding items suggests an alternative event starting from diagram A all the way to B, C, and D. So again, there are a number of advantages to the use of user level thread instead of the kernel level thread, including the following. 1, the thread switching does not require the kernel mode privileges. The thread switching does not require the kernel mode privileges because all of the thread management data structures are within the user address space of a single process. Therefore, the process does not switch to the kernel mode to do the thread management. This saves the overhead of 2 mode switches. That's user to kernel or kernel back to user. Secondly, scheduling can be application specific. So that's advantage. Scheduling again can be application specific. Now, one application may benefit most from a single or a simple round-robin scheduling algorithm, while another might benefit from priority-based scheduling algorithm. So the scheduling algorithm can be tailored to the application without disturbing the underlying operating system scheduler. And also the user level thread can run on any operating system. That's a good advantage. So no changes required. No changes required to the underlying kernel to support user level threads. The thread library is a set of application level functions shared by all applications. Now, what are the disadvantages? Here we say again, there are 2 distinct disadvantages of ULTs comparing with KLT. That's the user level thread comparing to the kernel level thread. So in a typical operating system, many system calls are blocking. As a result, when a user level thread executes a system call, not only is that thread blocked, but also all of the threads within the process are blocked, which we mentioned earlier. So that would be a disadvantage. And also secondly, in a pure ULT strategy, a multi-threading application cannot take advantage of multi-processing. So a kernel assigns one process to one processor at a time. Therefore, only a single thread within a process can execute at a time. In effect, we have application level multi-programming within a single process. Now, overcoming the user level thread disadvantage, here we say we can use the method jacketing. So another way to overcome the problem of blocking threads is to use a technique referred to as jacketing. Now, the purpose of jacketing is to convert a blocking system call into a non-blocking system call. So the purpose is to convert a blocking system call into non-blocking system call. For example, instead of directly calling a system IO routine, a thread calls an application level IO jacket routine. Now, within this jacket routine is code that checks to determine if IO device is busy. Now, if it is busy, the thread enters the block state and passes control through the thread library to another thread. So when this thread later is given control again, the jacket routine checks the IO device again. So this is our kernel level thread. Again, this figure shows thread management is done by the kernel with the kernel level thread. So again, in a pure kernel level thread facility, all of the work of thread management is done by the kernel. There is no thread management code in the application level, simply an application program interface to the kernel thread facility. Windows is a very good example of this approach. Also, scheduling of a thread is done on a thread basis. Advantage of the kernel level thread, a kernel can simultaneously schedule multiple threads from the same process on a multiple process. And also, again, the schedule take place in the thread basis. This approach also overcomes the two principal drawbacks of user level thread approach. First, the kernel can simultaneously schedule multiple threads from the same process on a multiple processes. And second, if one thread in a process is blocked, the kernel can schedule another thread of the same process. Again, another advantage of KLT approach is the kernel routine themselves can be multi-threaded. Again, the kernel routines themselves can be multi-threaded. Now, the disadvantage of KLT, here we say the transfer of control from one thread to another within the same process require a mode switch to the kernel. So the principal disadvantage of KLT approach comparing to ULT approach is that, again, transfer of control from one thread to another within the same process require the mode switch to the kernel. And the best method, again, here we say the combined approach. So again, some operating system provide a combined ULT, that is the user level thread, and kernel level thread facility. As we can see in this diagram, we have the user space and also the kernel space. So we have some thread. We have our process with some thread at the user level and also some thread at the kernel level. So some operating system provide a combined user level and also kernel level threads. So in the combined system, thread creation is done completely in the user space. In the user space, as is the bulk of the scheduling and synchronization of thread within an application. Now, the multiple user level thread from a single application are mapped onto some smaller or equal number of kernel level threads. So the programmer may adjust the number of kernel level thread for a particular application processes to achieve the best overall result. So in the combined approach, multiple threads within the same application can run in parallel on multiple processes. And the blocking system call need not block the entire process. Now, if a properly designed, this approach should be combined the advantage of pure user level thread and kernel level thread approaches while minimizing the disadvantage. So these are the different approaches, relationship between threads and also the process. So we may have one-to-one relationship, which means Each thread of execution is a unique process within its own address space and resources. This is normally Unix implementation. Then also we may have M2 which is many to one. This means a process defines an address space and dynamic resources ownership. So we may have a multiple thread may be created and executed within one process. Or we may have a thread may migrate from one process to process environment to another. So you have one thread going through two or more different processes. That's one to many. Then we have many to many, or MN, which means combine the attribute of many to one and also one to many cases. So we may have many process, one thread going through many process, or many thread in one process. So that will be the conclusion of our lectures. So again, the idea of having many-to-many relationship between thread and process has been explored in experimental operating system, which we call the TRIX, T-R-I-X. So in TRIX, there are the concept of domain and thread. So the domain is a static entity consisting of address space and also ports through which the messages may be sent and received. So a thread is a single execution path with an execution stack, processor state, and schedule information. But as with the multi-threading approaches discussed so far, multiple threads may execute in a single domain, providing the efficiency gains discussed earlier. However, it is also possible for a single user activity or application to be performed in multiple domains. So again, that will be the conclusion of our lectures. Again, if you have any question, you can send an email or post discussion in the campus. So again, see you in the next class. Thank you.